Alright, let's pick up where we left off in the last video. We're going to do a practice problem here using the equation that we learned in the last video. And then we're going to step into using that equation in a slightly different way. It really is the same way, but it looks different. The reality is that it's the same type of process, but the way that we use it is a little bit different, so it looks very different. But anyway, getting ahead of myself, let's go ahead and look at the question here. It says, suppose you find a penny minted before 1982 when pennies were almost entirely copper in the snow. How much heat is absorbed by the penny as it warms from the temperature of the snow, which is negative 8 degrees C, to the temperature of your body, 37 degrees C? Assume the penny is pure copper and has a mass of 3.1 grams. So we are trying to find Q. That's our goal here. What is Q? How much heat is the penny absorbing? And so anytime we're trying to find an amount of heat, it's a good bet that we are going to use this equation. Q equals mcs delta T. So if we go ahead and look at what else is given to us in the problem, we are told the mass of the penny. We're told that it is copper, and we're told that it starts at negative 8 degrees and goes to 37. So delta T is, let's see, be 37 degrees C minus negative 8. Because remember, it is final minus initial. So the final temperature is 37, the initial temperature was negative 8. And so delta T is actually 45, I believe, if I'm doing that correctly in my head. 45 degrees C. The copper is telling us which C sub S to use, what specific heat to use. And so if we go back to this slide here, what we can see is that copper has a specific heat capacity of 0.385 joules per gram degree C. Okay, so we have everything that we need then. We were told that we had copper, and so we found the specific heat. We were just given the mass in the problem, and we were able to use the temperatures that were given to us to find the delta T, the change in the temperature. And so that's everything we need to solve for Q. And so if we do that, what we'll have is 3.1 grams times 0.385 joules per gram degrees C times 45 degrees C. Notice here that grams and grams cancel, degree C cancels, leaving us with joules. And so the amount of heat that that penny absorbed is 53, let's see, we get, technically we're only supposed to have 2 sig figs, but I'm gonna cheat a little bit and give myself 3, 53.7 joules of heat. Now notice here, the number that we got is positive. That was not coincidence. It's positive because the penny absorbed heat. It absorbed heat from our hand. In this case, our hand is actually part of the surroundings because the penny is our system. So the penny gained heat, and so therefore Q is positive. Now, if you got to the end of this question, and actually I totally forgot to have you pause the video and try it yourself, but if you did that of your own volition and you tried to work it out on your own, and you got to the end and you found negative 53.7, what that means, most likely anyway, is that you have these two switched. You have the initial and final temperatures switched. Because if you swap those and you have a -8 minus 37, you'll end up with -45. So that's the most likely scenario if you have the wrong sign there. Which, by the way, is like if we were doing the opposite process, if you had the penny and it was in your hand and you dropped it into the snow and it went from 37 degrees down to -8, then that would be absolutely correct. You would end up with -53.7 joules of heat because your penny would have lost that much heat. But because the penny is gaining the heat, it is absolutely correct that we end up with a positive value for Q. Alright, I hope that makes sense to you all. We're going to go ahead and move on now to using the same idea, using the same process, but in a slightly different way. We're going to be looking at two different objects that are in contact with one another and are exchanging heat between the two of them. If you remember earlier, we said that when we have two different objects at two different temperatures and you place them in contact with one another, heat is going to flow from the hot thing to the cooler thing until they reach the same temperature. At that point, they're at what we call thermal equilibrium, when the two things have reached the same temperature. Because of this, and because everything does this, as long as you have two things of different temperatures and you touch them together, if you leave them in contact long enough, they will come to the same temperature. What this means is that they're going to have the same final temperature. So if we want to define each of their two things as their own separate systems and look at the heat that is being exchanged between the two, number one, they're always going to have the same final temperature. They'll have different initial temperatures. They have to, because if they don't have different initial temperatures, then there's no heat exchange because they are at the same temperature. So they have to have different initial temperatures, but their final temperature will be the same. And what's more, whatever heat is lost by the hot thing must be gained by the cold thing. Now we are making an assumption here, which is not a perfect assumption by any means, but we kind of have to make this assumption to make our lives bearable. And no, don't you go thinking that thought. What, you think chemistry is bearable? Yes, it is. It is bearable. In fact, it is wonderful. Anyway, moving on. If we don't make this assumption, our life gets a lot more complicated with these questions. So we are going to make the assumption that any heat that the one system loses only goes to the other thing that we're looking at. In reality, heat is lost to the surroundings all the time. There's waste heat all the time. But just to make our lives easier, we're going to say that any heat that the one thing loses goes to the other thing that we are looking at, the two things that are in thermal equilibrium by the end. So not only are the final temperatures the same, but the Q, the heat values, will be the same but opposite in sign. Whatever one thing loses, the other one gains. And so this is going to be very, very useful when we have a situation like this. Let's say we have a piece of metal that is at a different temperature than the water around it. We stick that piece of metal into the water. The metal and the water are going to transfer heat, just depending on which one is warmer, until they are at the same temperature. And so whatever amount of heat goes, let's just say, for example, that the metal is cold. And actually there are some, believe it or not, commercial products that you can buy where that's just a chunk of metal that is actually meant to go in drinks. They're kind of an alternative to whiskey stones. If you've ever heard of whiskey stones, where you freeze actual rocks. So you put rocks in your freezer, and then when you want to drink your whiskey and you don't want the whiskey watered down with ice, You stick a whiskey stone in there that has been frozen, and obviously the rock is not going to melt as it warms up, but it will still keep your drink cold. So it's kind of the same idea. You can get pieces of metal that will do the same thing. Although usually those pieces of metal have higher specific heat capacity material inside the metal, but that's kind of getting into the weeds. Anyway, let's say that the piece of metal is cold. Well, then the water would give heat to the metal, and however much heat the water lost, the metal gained that same amount of stuff. And so because the numerical values, the absolute values of those energies are the same, just opposite in sign, we can set the equations for those two things to be equal to each other as well. So we have a Q is equal to mc delta T for the water, and a Q is equal to mc delta T for the metal. And because the Q's are equal, just opposite in sign, we can set the rest of the equation equal and just make sure that one side or the other has a negative included. And just because of the way the math works out, it doesn't actually matter if the negative is on the water side or on the metal side. It'll all work out in the end. But in the case of the example here, they put the negative on the water side. It's a little bit confusing because then it makes it seem like this only works if the water is losing heat, but that's not the case. It'll work either way. The sign will work out properly. And so when we have two objects like this that are reaching thermal equilibrium or have reached thermal equilibrium, we can set those two things equal to each other. And if we have enough information about one side of the equation, we can use that to solve for something on the other side of the equation. So let's look at an example of that here. So we have a 32.5 gram cube of aluminum that is initially at 45.8 degrees C. It's submerged in 105.3 grams of water at 15.4 degrees C. What is the final temperature of both substances at thermal equilibrium? And we're going to assume that the aluminum and the water are thermally isolated. And what that last little bit there means is just that we're making the assumption that they're not losing heat to something else. The only heat exchange that is happening is between the aluminum and the metal. Or sorry, between the aluminum and the water. All right, before I ask you to pause the video and give this one a shot, I do want to forewarn you that the algebra on this one is a little bit more intense than what we've done before in this class. It is by no means crazy. It's not crazy algebra. It is high school algebra. But really up to this point, we've done the only algebra we've done up to this point has actually been fairly simple high school algebra. But the algebra on this question is really more just, there's a lot of it. It's not difficult. It's just a decent bit of algebra. So just to let you know, if you're working through this and you think to yourself, wow, that was really fast, probably did something wrong. There's a decent bit of algebra to get through this. So with that being said, and just again to remind you here, we're looking for the final temperature, TF, and the final temperature will be the same for both. That's one of the key things to keep in mind here, is that the final temperature for the aluminum is going to be the same as the final temperature for the water. So go ahead and pause the video now and give this question a shot. See if you can and work it out on your own. All right. I hope you gave this one a shot, and I hope that you were able to work it out. If not, or even if you did and you just want to see how someone else works through it, let's go ahead and work through it together. So let's first of all write down what we're given. So we are told that the mass of the aluminum excuse me, is 32.5 grams. We are told that the mass of the water, there it is 105.3 grams. And we are told that the initial temperature of the metal, which we're going to write like this, or Tim, is, let's see, that was 45.8 degrees C. And the initial the initial temperature of the water is 15.4 degrees C. And that is all the information that's given to us in the question, other than just the identity of the materials, which is still something that's important. And so if you remember, CS for aluminum was 0.385, if I remember correctly. Oops. Joules per gram degree C. Make sure that's correct. Yeah. Oh wait, no, that was copper. Sorry, not aluminum. Aluminum is 903. That will teach me to try to do things by memory. Okay. 0.903. Okay. Just I'm second guessing myself now. Yes, 903. My head was thinking 930. I tend to flip numbers around like that. And then the water is 4.18 joules per gram degree C. Okay, so we're starting with a lot of information here. We want to keep in mind, excuse me, that we're looking for the final temperature. And what we're going to do now is we're going to go ahead and set up the equation that we had back here, but we're going to leave the delta t's as they are. I'm just going to do that for now just because I know it's going to make it a lot easier for me because I've done this question before. I'm probably not going to have enough room on the page here if I expand delta t too early. So I'm going to go ahead and write everything into this equation, but leave delta t as is for now. So the mass of my aluminum is 32.5 grams. The specific heat of my aluminum is 0.903 joules per gram degree C, and that is multiplied by the change in the temperature for the metal, and that is equal to negative the mass of the water, 105.3 grams, times the specific heat of the water, 4.18 joules per gram degree C, times the change in temperature for the water. Now notice here that even though the final temperatures are the same for both, the change in the temperature is not the same for these two. The change in temperature for the metal is different than the change in temperature for the water. So what I'm going to do now is I'm going to try to make this as simple as possible. So I'm going to go ahead and multiply these together, and then simplify everything to one side, essentially. Simplify all the numbers that I have to one side. So at this point, just to talk about units, my grams have canceled. So I just have joules per degree C right now. But if I go ahead and do the math here, so I have 32.5 times 0.903, that gives me 29.35 essentially joules per degree C times delta T for the metal. And then I have negative, let's see here, 105.3 times 4.18. Oops, I typed that in wrong. Where did I do that wrong? There we go. 440.2, we'll say. And that is also joules per degree C times the change in the temperature of the water. Sorry, I got a frog in my throat for some reason. Alright, so all I did here was just simplify the numbers that I have, so I'm going to keep doing that. And what I think I'll do is I will move everything over here to this side. So I'm just going to divide both sides by negative 440.2. So when I do that, this is just going to go away on this side. And just for the sake of space, I'm not actually going to write that in, just because, again, I know I'm limited in terms of space here. So what I'm doing in this step is I'm dividing both sides by negative 440.2. So what that means is I'll have 29.35 divided by negative 440.2, and that will leave me with negative 0.06667 delta Tm. And notice here that my units are gone, because I had joules per degree C, and then I divided by joules per degree C. So I am unitless at this point with this number, but I'm going to have units inside of delta T, so don't worry about that. And that is equal to delta T for the water. All right, now I'm going to expand out the delta T. So I have negative 0.06667 times TF, the final temperature, minus the initial temperature of the metal, which was 45.8 degrees C. There are those units I promised you. And that is equal to delta T for the water, which is TF, the final temperature, which again is the same for both. They both have the same final temperature, minus the initial temperature of the water, which was 15.4 degrees C. So I'm going to do a little bit more algebra here. I'm going to go ahead and factor this in here. So I'm just going to multiply TF and negative 45.8 by negative 0.06667. There is a there's a term that they use for that, and I cannot remember what the mathematical term is essentially, but we're just multiplying everything inside the parentheses by this number here. So we'll end up with negative 0.06667 TF minus, actually that'll end up being plus, because we're going to take negative number times a negative number. So that is going to be 3.05 degrees C. So all the rest of that is still the same. So now I have on the left and the right one value of TF and one value with a degree C. So I'm just going to separate those two. So I'm going to move all the TFs to the left, all the degree C to the right. And I'm going to do that by, actually let's do the opposite. Let's move the TFs to the right and the degree C to the left, because I think that'll make more sense. You should be able to see what's happening a little bit easier that way. So I'm going to add 15.4 degrees C to both sides. That will essentially cancel out this 15.4 and add it to the 3.05. At the same time, I'm going to add 0.06667 TF to both sides. And so what that will end up doing for me is I will have, actually I don't know why I need to do that on the calculator. That was fairly simple. So I'll have 18.45 degrees C is equal to 1.06667 TF. Now if you're wondering where did the 1 come from, that was this. This is 1 TF. So I had 0.07 essentially TF that I added to 1 TF. And so then to finish this problem, I'm going to divide both sides by 1.06667, and that will give me the value for TF, which is going to be just a little bit less than 18.4. Well, a little more than I thought it was going to be, but so 17.3 essentially degrees C. Phew. Decent bit of algebra there, and I couldn't even show it all to you because I was, like I said, I was going to run out of space. But hopefully, I explained it well enough that you could see where I was going with each of those steps there. Real quick before we finish up this video, because we're not going to move on to the work stuff yet in this video at least, I do want to point out that there is a quick and easy way to, at the very least, make sure that the answer that you got makes sense. And the easiest way to do that is to see if your final temperature is between the initial temperatures of the two things that are now at thermal equilibrium, because that will always be the case. The final temperature should always be between the two initial temperatures. The hot thing cooled down a little bit, and the cold thing warmed up a little bit. And so the final temperature for both should be between the two initial temperatures. There's no way for us to tell exactly where it should be. If you've done it long enough, like I have, you can kind of get a good idea. But for you, I do not expect you to be able to just eyeball where it should be, but you should know at the very least it is in between. And that is the case for us here, because the water was at 15, the metal was at 45, and 17 is between those two numbers. And so at least in that sense, this answer makes sense. All right, we will call it there for this video. In the next one, we will take a brief look at one particular kind of work. So I will see you in the next video.